Hello everyone again. Um, I'm I'm thankful for you guys joining because it's an interesting topic that I think I'm gonna bring up and discuss with you. And it's an emerging technology still, and I'm not afraid or shy to say that it's emerging because obviously the world is fragmented and technology advances are somewhat fragmented as well in this new AI era, still new, but I am more or less confident that we're still in an emerging technical area where the leaders have not yet been defined. The core architectures have not yet been defined. I mean, implementation architectures of the system. And therefore, it's more fun to be part of something which is not that formally regulated, where a new opinion can disrupt the entire establishing approach base. But let me quickly share who I am here. Obviously, this is an AI generated image just for you to smile. In general, my current title is AI Engineering Director because recently I've been transitioning into AI R&D team within Ciklum. Previously, my role was in so-called solutioning team, where we basically allowed the largest customers of Ciklum to start their cooperation with Ciklum in a most efficient manner. My job was to make sure that whatever solution architecture, cloud architecture is defined, it's defined up to the most modern standards, up to the best interest of the client. I was technically facilitating all of the aspects of the new large clients onboarding with Ciklum as part of solutioning team. Previous to that, I've actually been with the company since 2013, started as a .NET team lead and most of the time spent as a team lead architect and then in solutioning team. But it doesn't matter that much because we're here to discuss a niche topic, and that is how to build agents that do operate in turns. The agenda slide, I think, use it as a reference when you get the presentation. I'm gonna briefly give you some portion of theory behind what are agents, what is React paradigm, but most of the time we're gonna spend looking at the terminal where I run, I think 8 Python scripts, which represent an agent, a proof of concept, almost like very POC-ish size agents. But nonetheless, we're gonna review the operation of the systems like this from various perspectives. We're gonna use several models and several frameworks which allow us to use AI models. So I hope you are somewhat energized to bear through at least 40 minutes of looking at the code and the terminal. So what is agent? Wikipedia probably has the definition already. The content on the slide, I think it comes from my opinion, that it's an autonomous system that is able to reason, act, and learn to achieve the goal that has been put forward in front of it. The key characteristics of the agents, at least at this stage of the agents that matter, to put it this way, is access to tools, its iterative nature for problem solving, and obviously agents that we are interested about are powered by LLMs. They're not deterministically coded applications. Otherwise, it would just be a computer program, a tool. Well, agent is a computer program, but the non-deterministic part of control flow being controlled by LLMs is what makes it an AI agent. By the way, link graph, which we will not be reviewing here, as I want to give a very basic understanding of what powers the link graph, Crew AI, and other agents under the hood. Defines modern architecture for agents is that agents need to do tool calling, have memory, and do planning. Well, we're gonna see all that. At least tool calling and planning is the largest focus at the moment. But like I said, I'm not going to be showing you access through wrapper agent implementations. We're not going to be importing some library. We're going to use like bare code variables for loop to actually simulate the agentic operation. So React a paradigm which is currently used. You might see a lot of articles about it on Medium, a lot of videos on YouTube. Some might say, okay, Max, React is spring 2025 or even winter 2024. The relevance of the paradigm still holds true. The modern tools which are competing in agentic coding space, like OpenAI Codex and Claude Code, they are all actually doing React. Some of you who are super experienced in that might even know more than I do about the paradigmic approach of those coding agents. But in general, we know that we give a complex task to an agent, and those agents achieve it through series of reasoning, acting, reasoning again, until they conclude that the task that was initially requested by the user is completed. That is basically what we will try to mimic in, well, mimic is the bad word, because mimic actually is almost like a deception. Mimic is about lying. I might be wrong actually philosophically, but we will not mimic. We will write that code that tries to actually implement that paradigm. And by the way, transparency is something any agent application developer, we should try to achieve it, although we're not obliged to have transparency exposed right in a chat window. So yeah, I briefly talked about this, that in the most, in an enterprise environment, whenever you are a part of the team building an agent for your client, you probably will not be building agents from scratch. You will have your AI solution architect basically suggest the agentic framework to use. Some of the like moonshots who are really aiming for the stars with the implementations might go with a more complex from scratch implementation, because AI companions are also very capable now in writing agents as well. But I think LangGraph is very well known. There are other frameworks. At work, you're going to do this. The purpose of the call today is to actually try to see under the hood of that and conceptually understand how those things work. So for LLM thinking, the model is very important. All of the demos I'm gonna show you today, those are gonna be locally running demos. I'm gonna use Llama for primitive cases and Llama CPP interface to access a locally downloaded model in Google format. I'm gonna rely on 8 billion and 12 billion parameter models. So not super smart, but the generation of the model, how modern and capable it is, basically defines how well your agent is gonna operate. In a production environment or in an enterprise application, you're most likely gonna be coding against the Cloud Inference API. So unless you're doing some fine-tuned small language model development, which would be very interesting, it's a completely different topic, inference on the edge. But yeah, model is important. I've learned this even while preparing for this knowledge sharing and while preparing for my larger project at Ciklum. And but to conclude, even small models of 8 billion parameters, if they are modern tool calling or multimodal models, they are very, very capable. Older one, 2024 one, might give you trouble. You'd have to do an extensive prompt engineering before you can get the behavior from the agent you'd like. The more modern model is, the easier it is, because it simply becomes your smarter assistant. So let's go and review the operation of the most primitive agent. I think I'm gonna start with running the agent, and then we're gonna dive deep into the code. Guys, throughout the demos I'm gonna carry out now, the questions will pop up in your head. Please write them down, because there will be a portion of those that I will cover in the subsequent demos. I have 8 of them, and each one builds on top of the previous one. And for the questions which are remaining, meaning I never touched them or describe the answer, we will actually read them out loud and discuss. So let me go back to the terminal. I've been running the test, so as you can see, I'm in Python virtual environment. And by the way, a few words. Uh, we we have these fun chats in Ciklum inside technical groups. Most of the people will probably still try to build agents, or at least the core inference part with Python, because it almost becomes a question of fashion. Some models, by the way, are actually built for special inference mode, where they know that it's going to be a Python runtime that cooperates with them. Um, my demos are in Python, but my background is more .NET, and I just want to say a word that you can write agents in different programming languages. It's not like Python is the only language for writing AI. For ML, it's obviously a go-to choice. But for AI agents, which are applied application programming thing, basically, you can use whatever you want. Well, the backend technology, obviously, we're at least discussing that for now. Although you can write agents, I believe, in front end JavaScript and use web LLM, which will run in your browser. So Python is not prescribed. Python is not mandatory.
I have a question like you have mentioned that we can do code and programming of we can use any programming language to create agent. We can use JavaScript as well. But what I have seen that many people prefer to write agents code in only Python language. Why if that so happen?
I think that like I said, it's a matter of fashion. Python is a language which easily gives you access to streamlined execution. It has a lot of already available libraries which you can tap into. Python models are in abundance, which are related to inference. Therefore, it's almost becoming a go-to language when you do anything AI. But that's not mandatory. You can easily code in JavaScript, .NET, and other languages. So again, I might not be providing a very exhaustive and confident answer. It's just because infrastructure around Python is very developed, and usually you will find things you need as Python modules. But still, I believe quality agentic solutions will arise not being written in Python. That's my opinion. Um, let me proceed, and we'll get to the questions at the end, guys. So, and again, it's the end of the day. Try to keep it light, especially when I switch to source code. I will only focus on the points of interest in the source code. The files we're gonna deal with are not huge, but try to bear with me. But also, if you don't understand something because I failed to explain it vividly, don't worry. We're going to share the files with you. And if you liked what you see in the demos, not the first one, I think the vivid demos start with the script 3 or something. You'll know what I mean. Um, if you like to know how it worked, what you will see, you will always be able to retrospectively take a look at that. So I suggest focus on looking how those agents work, what they write in the terminal. Don't try too hard to understand source code, because you can always sit down more comfortably with more time and review the source code, which we'll share. So I'm gonna call a file, which is a Python script. Its name is 1.agent.py, and I'm gonna pass it a parameter, which is a string, which is what is the current time. That's all. Let's see what it does. Okay, let's review it. And sorry, I'm gonna try to zoom in the text, because okay, that's better. So it showed us two steps. Um, it basically says LLM output thought. To find out current time, I can use a tool that provides this information. And it says action, run shell command, date, blah, blah, blah. Um, then it has a similar reasoning. It basically says observation. Remember this, observation, because I'm using this term as a prompt engineered output for all the tool calls. What important is that under the hood, this script has just executed the command in the terminal, this command, and the output of that was this. It was recorded in the output. On the second, and it all happened within one step. There already have been some sanitization problems because there is action here and action here, but this system, the way it's coded, has actually correctly identified that there needs to be just one tool call. That might be a log of the tool call, by the way. We'll see it in source code. So on the step 2, LLM is thinking, the observation is already in a readable format. No further action is needed. Final answer, 18:19:42, which is the time at where I'm at right now. That is the final answer. And the result of the execution of the script is this. This is very primitive in order for me to show you the most primitive implementation of agent, which already has the loop of think, act, conclude, but it doesn't have all the other features which we're going to discuss. And we're going to discuss safeguards, review of the final results, styling the output, and more low-level way of interacting with LLM. But let me switch to the source code of this and basically show you how this was possible. So I do not want you to try to precisely understand everything in this Python script. Most of the logic is at the top. The execution, the main entry point is at the bottom. Try to bear with me as I explain it. Run shell command is a Python function, Python routine, which accepts one parameter, and all it does, it utilizes the sub-process, which is a standard Python way to run processes on an operating system. It's basically a terminal accessible from Python, and this function is basically call whatever command is there. Then there is a custom object, which basically has a dictionary, a string, which is the name of this command. It could be whatever. I could have named it whatever I wanted. And it says that's a dictionary that points to that Python function. And by the way, for those of you who are Python experts, each programming language has its own terminology. My background, as I said, C#.NET and JavaScript, React.js. Therefore, when I'm describing you the Python constructs, although it doesn't prohibit me from explaining what the code does, I might be misusing some terms. Who knows? Maybe in Python it's called routines. Probably not. So please excuse me for that if the terminology is off somewhere regarding Python, but it doesn't matter for our purpose here. The third part here is the system prompt, and as we will see, the agents which are more capable and robust, meaning stable, they usually require not one but several prompts, and the informativeness of your prompt is what defines the success of the operation or failure. Modern large language models are very capable, and someone said you can almost talk to it like you're a caveman and it will still understand what you want. Well, the models which we're using, which are 8 billion parameters ones, basically capable of being ran on a computer with, if you do CPU inference, you only need 8 gigabytes of random access memory to run those small models. So basically, those models are not smart. Therefore, you need to provide a lot of babysitting in your prompts. For this very basic agent, the prompt is simple. I'm basically saying you are an AI agent that does React. For each step, do thought, action, or provide final answer. I'm trying to prompt engineer the tool calling here via action output. Don't worry, this is one way which I find very efficient with older models like Llama 3.1. And I'm going to show you an example when I switch to my last demo of how you use Llama CPP and try to work around the model's intrinsic tool calling facilities. So this is almost like, for those advanced of you who understand this, I'm almost cheating. I'm talking to an LLM in plain text, and some models are trained specifically for tool calling. And when you read the releases of new models, you might see the model vendor emphasize, "Oh, this new model is very advanced in tool calling." Well, that's not because it would output the action, semicolon, and the command efficiently. That's because its internal token-based um, facility for suggesting a tool call as an output of the LLM inference is coded very well. I'm going to show you the example of that, but that's more about your engineering of your inference process, not about your agentic behavior. So it slightly deviates from the main topic and the basicness of what I'm trying to deliver here. Anyways, system prompt is simple. I'm basically saying, "Hey AI, either do a thought, action, or provide a final answer." Um, Get LLM response is actually the function where I pass the history, and this call is important. By the way, I failed to say that in the first few prompts, I'm actually using Ollama. Ollama is a tool, and again, I don't want to turn this into an Ollama and Llama CPP related knowledge sharings. Ollama is a computer program installed on my current computer, which is listening on TCP endpoint, which allows other computer programs to communicate with it. Ollama will handle and does handle model loading and actual inference for me. So it's a comfortable interface to talk to AI models, passing them the which model I want to talk to, the history of the messages, and getting a response. I am not sure that a more serious implementations will ever rely on Ollama because it's a software dependency and it's for for user computers. But Llama CPP example, which we'll get to, is more of a low-level, more efficient programmatic approach of communicating with models. So I definitely see applications and even server applications relying on Llama CPP for inference. And by the way, what I'm giving here does not represent Ciklum's position on building AI agent. And I know you don't want this bureaucratic disclaimer stuff, but the area is developing rapidly. In Ciklum, we have multiple clients, well, numerous tenses of clients who are doing AI projects. And we hire dedicated AI engineers and deploy them on those projects, and they develop agentic systems on their own. My job in Ciklum, and I'm lucky to be in this position, to try to collect the information how in the company we're doing agentic development and provide options for that. But for the purpose of this knowledge sharing, the info is coming from me and is my subjective opinion of that. So don't, whatever you see here, I know you will still feel like, "Oh, he's from Ciklum, that's what Ciklum says." And it's not bad stuff I'm teaching you here. It's just Ciklum is, I'm not Ciklum. Ciklum is much more than me. You've seen we have 4,000 people, and many of them are already involved with AI development. Okay, sorry for this disclaimer. So get LLM response, you'll see it in all of the scripts. And by the way, it doesn't mean that I'm going to spend this amount of time explaining you each of the 8 scripts. It's important to talk about this one because others build on top of that. And they all add additional functionality layer, which make the agent either more robust or show the different aspect of operation. But all of them share the core stuff from this. Run shell command is in all of them. Get LLM response is in all of them. Parsing the output from LLM is something you inevitably will have in your source code because LLM will still provide you the structured output depending on how you use it through Ollama, Llama CPP, or different. Maybe you'll use Onyx runtime to do a model inference on a Microsoft model, but you will still do parsing. The more low level the tool you use is, the more babysitting of tokens and work with tokenizers will be required. It's a bit more advanced. I don't want us to deviate from the main topic of this, but in some form or another, you're gonna have to do parsing. And here I'm showing you the primitive parsing because it's an easy start. I'm basically trying to see what did this AI give me? Did it give me a thought, an action, or a final response? That's all you need to know at this point. So the entry point here is basically to run agent and pass the parameter I sent it. And run agent, you can shape the maximum amount of steps you want just for security, because the execution, by the way, is non-deterministic. You don't know whether two subsequent runs will give you the same results. So let me run this again and then go back to the code to actually review the for loop. Yeah, see, this agent almost provides an identical response all the time, although thinking is slightly different. We're lucky about that, because other agents with the more complex queries, you'll see that some of them are very successful from few steps, and some of them drastically fail even if they try to do 10 steps. You cannot actually predict that every run with the same input parameters will be the same. So when we run the agent, we collect the history object, which shows who said what. We try to say that system provided system prompt and user provided the initial query. Then we start the for loop, in which we're going to do iteratively um, step actions, either thinking, calling the action, or proposing the output. At the beginning, our history just contains the system prompt and the query, which was passed as a parameter, and we get the first LLM response. And then we try to destructure the object, which was returned by parse output, which we've seen here. And we basically see if there is a thought, we print the thought. If there is a final answer, we print the final answer in return. But if there was a thought and maybe an action call, we're gonna try to call this action, which ultimately will lead, if we were to attach the debugger, will lead us here, and it will call this action, and it will record the results of the execution of the action as if the user said it, and added observation, and here is the observation. But ultimately, observation is the result of this tool call on the current system. And we pass this back, because all we're doing is we're enhancing the history by new stuff. We're basically enriching the model's context and keep on passing it to the model again to call get LLM response. And at some point, LLM will see all of these discussions we had, and it will say, oh, I'm ready to output final answer, because everything needed to respond to an initial query is already there in our discussion. That's how it actually works here. It basically says, step one, do the action. Once the action is called, it goes into step two, but it already sees that the current time is already in the chat. Therefore, all it has to do to answer the initial query is to output the time. That's a very primitive agent, and maybe it would have made sense to stop here and discuss questions, but I promise you that many of those questions which are still in your head will be answered in subsequent 10 to 15 minutes. So please bear with me. We'll discuss all your questions at the end. As you have seen, the steps outputs were appearing not as you would expect from ChatGPT or whatever. So the second script I have is just to show you the streaming capabilities, which are also available when you do inference through Ollama. Basically, I'm trying to evolutionize the system prompt here, but it doesn't matter. I'll get back and explain important parts of this evolution. You just can see that system prompt has grown. But all I wanted to show you with the second script is that when you call Ollama chat and say, hey, Llama 3.18b, here is the message history, we pass a parameter stream through, and therefore we can read the stream in chunks and output it. Let me show you that. So what are the files in the current directory? And this is, by the way, a complex query. They're often fail on this. But look, I think it already Yeah, final answer is fine. Wow, we are lucky today, guys. So basically, I have given it now a different prompt. It's not hard-coded in the script. I'm basically saying, hey, agent, what are the files in the current directory? You might have noticed that the text did not appear boom, boom, boom. It was appearing as it was basically returned by an LLM, and the speed of inference is determined by the capabilities of hardware I have. So it did the tool call. Now it did the tool call ls-l to list the files in the current directory. It basically, the Llama model knows that in order to satisfy this query, which is list the files, usually this works. And it returned the command it returned a like prompt engineered token action, and our script picked it up and ran this command. And when it got to step 2, it observed that the stuff needed to answer the question is there, therefore it just produced the answer. And final answer is pretty good, actually. It basically says there are 10 files in the directory, and here are those files. Um, Perfect. I think it worked well. Let's move on to script number 3. So um, this, by the way, the script was made with the help of Gemini CLI. It's just an interesting, at least to me, peculiar aspect that some of you who have tried working with Gemini CLI know that its UI is very different from Claude Code, for instance. And when I asked Gemini CLI to actually introduce styling to the agent, to the demo agents we're dealing with here, it produced the styling, which is, yeah, I know that for Python, you would usually go to the rich library and use that. But the output is very similar to Gemini CLI. So if I were to go almost religious here, I would say that Gemini CLI created an agent which resembles itself. But it's just a coincidence, actually. It doesn't mean it has some intrinsic knowledge for that. So let me run the styled uh, version of the same thing. It has the same prompt as the script number 2, but now throughout the code, we have console print commands, and we're using the rich library, which is basically just styling of terminal output library. We're calling different constructs of it, like panel, you'll see it, to make the operation more vivid. Um, so let me call that Python 3 dot, and what we're gonna do, count files in the current directory. Of course, you see, it just prints the stuff more nicely. It now has a designation for LLM output, the thought. It shows the action that it took. It shows the observation and the final answer. By the way, I have I don't have a strong belief that this is correct, but no, that is correct. If we do a last cell and see, no, it's not. A probably, yeah. So in the current directory, you've seen we previously saw these like 10 files, but there are also other virtual environment, Git repository. So I'm just explaining you where this number comes from. It's 4,014 files, including the hidden directories, which are under this directory, but are not explicitly shown by a list. That's for those of you who are familiar with Linux-based operating systems. You understand what's happening here. So the purpose of the script 3 was to show you the more nicely styled file, no more than that. And I think it basically gives us, and by the way, at this point, when I was preparing these proof of concepts for you for this event, I was already pretty amazed how a small Python script powered by Llama is able to give us an agentic behavior in which LLM decides what to do. Our script does it programmatically, passes it back to LLM, and it basically makes a decision. Oh, is the task solved or I need to do something else? It's already working with what? How many lines of code? 132 lines of code. when maybe 15% of it is styling. I think that's pretty amazing how LLM covers, like we get a lot of value from this little agent. It's a demo value. I know you don't use it in production, but it's still a lot in comparison to conventional software development. And it's just a few lines of code because LLM is able to do that. So let's briefly talk about another aspect. You like I suspect most of you are aware of the term context window. Context window is basically a size of text that a model is able to work with. Context window includes any information you input into the model and its response. So for instance, if we were to say that there is a tiny language model which can only work with 100 tokens. And token is roughly like between 2 to 4 words, because again, I will spend precious time here explaining what tokens are. Look it up if you don't know, but in general, we just calculate token context windows in tokens, and tokens are usually not one, but a few English words. So if we have a model with a context window of 100 tokens, it means that if we are providing a large question to it and occupying 98 tokens, it only has 2 tokens to respond, and it most likely will simply fail. Therefore, any agent which does iterative work needs to be aware, at least the application needs to be aware of the context window. And those of you who used coding assistants or other agents, you know that there is such phenomenon as compacting the conversation in order to compact it into a smaller piece of text, therefore freeing up some portion of the context window. In this example, I'm doing at least the context counting, but it's not obvious which are the easiest way for it. And yeah, or you probably could have used the inference facility for context calculation. But in my case, I'm just giving an example where you remember we have this history, and history object, as we talk and steps are executed, we're adding more and more history through history.append. And therefore, after each step, we can calculate what percentage of the context window is utilized. Therefore, when we're approaching the end, or like Claude Code allows us to usually use, I think it's 80% of the context before it forces itself to do compacting. So here I'm just implementing a demo where through Llama, I'm getting the context window size for a particular model, and then always calculating what amount of context window is left. Let me show this to you. So Python 4 dot context what files are in the directory and what are they? So I'm specifically giving it a question which will force it to go into many steps until it fails. This will not work with the primitive agent we have, but this will allow me to show you the tracking of context window utilization as it keeps on thinking. It already this script, by the way, has sometimes problem with parsing the output, but we don't care what's happening. As I told you, I know it will fail, but as you can see, we already are occupying 2% of the context, and as it will continue to read those files, trying to do stuff, I will need to stop it so it doesn't mess up my system, so that I can continue this knowledge sharing for you. But in general, we can continue counting the context window utilization and do something when we're approaching the milestone. Oh, I hope it max steps reached. Oh, yeah, I see. Like implicit safeguard. So I don't know how much you are still following me, but this was an example how one could keep track of how much of the context window is being utilized. This is like a poor man's approach to tracking because we're doing this in our application code. Well, and it's not given that other tools are not relying on the similar approach. If you know a different one, a more advanced one, I'd be happy to hear it. I know it's not a secret. It's just the review nature of this knowledge sharing event doesn't require me to go too deep into context window management topic here. So there is an important aspect which I wanted to specifically show you, is that so far you have not seen a true React because we did not introduce phases into our agentic procession of the query. So it was very often that I ran these test agents and that they were giving me a bad response, even though the information in order to give that is required to give a good response was already in the context in our history. Therefore, this script number 5, it adds an interesting aspect, and that is that if the LLM has provided us the final answer before returning the final answer to your user who actually raised the query, asked the question, we're making one more turn programmatically. We're going back to LLM and basically saying, hey, you told me this is the final answer. Here is the initial query. Here is the history. Tell me again, are you sure this is the good answer? If you have the better one, provide it in the better answer element. This way, it's another safeguard, like, those agents usually print nice summaries, and you can always see it go much faster than it did when it did reasoning and action calling. Well, this is a programmed in approach to make sure that the final result is more or less one more time reviewed by an LLM. And I can assure you that this is not redundant because it was very often when final answer provided by the same model was later on much more enhanced by a better answer. Let's see if I can come up with an example really quickly. Directory, and I'll do. Is it 5? Yeah, let's see what happens here. Right now, I'm hoping the model is gonna behave badly. No, it doesn't behave badly. Not yet, at least. Let's see. Because a final check is is a programmatic approach which saves us when the model is thinking in the wrong direction. Um, yeah, it's gonna confirm. So here is what happened. The agent you've seen previously has came up with a final answer candidate. It says, since this guy asked what files are in current directory, here are the files. And I'm doing the final verification. I'm saying, hey, model, this is the chat. Is this the final answer? And it did not come up with a better answer. Therefore, the final result is actually what was initially suggested as a final result. If this had a nonsense or a hallucination, very often final check actually helps us with that and makes us arrive at the good result. I know that, we still have time. Cool. We're going to have more time for questions, guys. So, one more thing. You've seen me just now be a little scared that when it was doing this, context checking, I said, I will need to stop it before it breaks my system. So, you know about the concept of safeguards in agentic behavior. Safeguards might be any conceptual like behavior control for the AI, whether it's not allow AI to produce prohibited content, not violate company policy. Here, I'm trying to give an example of the agent agent logic, which has this I will call everything interesting because that's the point of interest. That's what I want you to be interested in. So I'm defining a function called isCommandSave here. Whenever LLM will suggest to make a tool call, I will make another trip to LLM saying, hey AI, I'm about to make this call on my operating system. Just tell me, is it safe or not? And it will give me the answer, safe or not. I'm actually saying, is it possible that this command will damage my system? And it will say possible or not possible. And only if it's not possible, it will proceed. Let me intentionally try to get it to remove something, and maybe it will catch it as a system breaking behavior. It's script number 6, sorry. Python fix, remove all .md files from current directory. I, by the way, never run this command. I just came up with it, so I don't know what's gonna happen now, but it's still gonna be fun to watch. Yeah, interesting, cool. So what it suggested, and oh, by the way, I thought the moment LLM suggests the dangerous command, it will simply fail. Okay, let me tell you what happened. I hope you can bear with me. So AI suggested to call a Python function called run shell command, which you've seen, and this is the Linux. It's also applicable for Mac OS, which we're on right now. It basically says find by name all .md files and delete them. And my check was to basically ask LLM, is this possible that deleting this will damage something on my system? And Llama 3.1 is smart enough to basically say, yes, it is possible. Although we don't know if it's possible, it's just an MD files, but who knows, maybe my internal scripts are linked to MD files, which provide file saving policies or whatever. So in general, I'm very satisfied with this demo now because it has shown us how the safety check, and by the way, I own you showing a bit more of code because guys, I know that I'm jumping in the code. It's we would have run out of time and we would still be probably on script 3 if I were in detail describing you every line. I strongly encourage you to look through all of these Python scripts retrospectively. But basically, if this code is important. Oh no, it's not here. Hold on, let me. Please come on, save. Yeah, here it is. So safeguard check. So we do a tool call, and if the tool name is run shell command, it cannot be anything else because that's the only tool we're passing it. We're gonna check whether it's safe or not, and only if we don't go into this error clause, which will cause us to call continue on our for loop. Only then we will do this call, which is actually executing the command. So these lines here is an example of a safeguard in an agent code which does not let AI agent to harm your system. This can be anything. That's how Google or any other vendor filters their prompts. And well, maybe that's not a fair statement. We don't know whether, well, I don't know whether the safeguards and policies are a part of the system prompt of the LLM. I'm just showing you one way to implement those system prompts in your agentic behavior applications. In most cases, when you code for your clients, you will also be coding agent behavior, probably not fine-tuning models. Therefore, this is the way to achieve the business requirement if there is one. Yeah, that's all for the safeguards. Strongly encourage you to review and maybe even debug the code to see how it works, but nothing super specific here. Let's move on to the final two Python scripts I have to show you. And let me see if this one still relies on Ollama, but like remember our previous prompts. Let me go back to it. Our prompts had this part. Your response must be in the following format for each step. Thought, your reasoning process. One of the following elements. Action for tool calls or final answer. That is me using prompt engineering to simulate tool calling. This would work even with the models which are not trained to tool calling. But this, maybe I've said it, I'll say it again, is a form of cheating because model developers are creating embedded, baked-in facilities for tool calling. And let's try to review what those are. Depending on your inference mechanism, that's a broad term, speaking philosophically, in the script number 7, for me, it's still all llama. But I'm dramatically changing how I am doing the cooperation with Ollama. By the way, let me show you my LLM completion here. So previously, I would say Ollama chat and pass it the message history and get a response. In the file number 7 and in 8, as you will see, I'm utilizing several prompts, but we'll get to this. But my me calling the LLM has also slightly changed. Let me show you. And no, that's not it. Hold on. I'm also calling no, and then it means it's changing its script number 8. Sorry guys. So here we're still at least for the first phase, we're still in all llama chat. We're calling the same mechanism and passing it the planning history. Yeah, let me actually walk you through this. Please bear with me. So in the file number 7, I tried to introduce two distinct phases of agent operation, the planning phase and prompt acting. And I'm basically saying, create a plan how to achieve the user's query. And I'm using this prompt. It's called system prompt planning. It's just a variable name. And I'm getting the plan from the LLM. That's it. That's all it happens. I'm just giving it a query and getting the plan back. Then I pass on formally to phase number 2, which is execution. And I'm adding a different prompt here where I say, you are helpful AI, you have the plan, follow the plan by making a tool calls. I want to force LLM to return tool call suggestions because planning is one phase, execution is the other one. It is crucially important. And by the way, if you get to review this, and this is more advanced than the previous files, by the way, but without this example of populating the tool calls array, I was not able to get Llama 3.1 to give me the proper tool calling beyond actual text. And with this one-shot example, with one example, it's a future prompting, one example, I was able to get the LLM to actually return tool calls in a dedicated part of the return object. Let me show you, and then we're gonna run this one. So we're passing it, we're calling the model also through Llama chat. We're passing it the history and the tools available. But let me show you how we're dissecting. So the Llama.chat gives us a response. Response is a complex object. And from this response, we're extracting an assistant message, which basically just getting the message. And from the assistant message, which is also a complex object, we're trying to get a structured part, which is called tool calls. I know it's not very vivid from the call, but if you do the debug, you'll understand that we remove this formality of asking AI to return tool call in an action part. So remember here, I was asking it, if you need to do a tool call, return this text. I invented a token here, action, and I was asking it to return a token. Here, I'm not asking that. I'm just giving it an example how to return it because that's the Llama 3.1 template for tool calling, and I'm reading it from a structured object. That's I think that's more important for you to understand that in a more mature. So for proof of concept, any approach is good. Especially, it's amazing how prompt engineered tool calling works pretty well. Maybe not for the super complex multi-step tasks, but still for multi-step tasks, it still does. But whenever you do a mature engineering with tool calling models, you will need to understand how those models do tool calling suggestions, and you need to read them in proper way. So here, this is one example, but it's very baked into Llama, all Llama. I'll explain script number 8, which is the most low level Llama CPP type, and I'll do a demo of it, and we'll move on to questions because some of you might have a hard stop. Um, Sorry, we're out of time. Uh, in the script number 8, which is the most mature demo agent here, we have 3 phases, therefore 3 system prompts: planning, acting, and synthesis of the response. I'm no longer using all llama. All of the previous ones you've seen me import all llama. Here I'm importing object called llama from llama CPP module, which is a different library to do model inference. In order for it to work, I need to pass it the locally downloaded model file. Model files come in different formats. Like I mentioned, we're using JGoof format here. I basically went to Hugging Face, which you know is the basic repository registry for open source models. Well, at least publicly available models, not all of them open weights or open source. So um, I have this file downloaded, and I'm loading it through the power of Python. I'm loading it with a call to llama object, and I'm basically trying to make all of the functionality of the model available in LLM through LLM variable. Later on, I'm doing executions here. Everything happens through LLM parameter passed into run agent, and in here, um, there. So this particular combination, Llama CPP, and which is the inference mechanism, and Llama 3.1, which is the model, there is an existing bug in Llama CPP which makes the model return tool calls as JSON in content field. You learn this by inspecting the documentation of the model and your inference message, and you write your code if you need to work with this model in accordance to what you learned, how you can get the tool calls mechanism. We don't have time for me to digest this completely, but all I'm saying is that and calls here, like parsing here, is it will be different for each model, um, but it is the most efficient way to remove guesswork from did this model wanted to call a tool, did it say it in plain text or whatever. Here we are more formally almost arriving at a token level, where the model is saying my response is not text, my response is a tool call which you need to make. And then once we parsed the tool call suggestion, we actually do a tool call. I know you guys, you're tired and probably eager to get to the questions. Let me run the script number 8, and we'll get to the questions in a more live discussion. Files in the Iron directory, and what yes, what those do based on their names. Goodbye, summer. You see a slightly different interface with this. By the way, those system messages of loading a model through Llama CPP, they can be suppressed. In step one, which is hard-coded planning step, it came up with the plan. It suggests that I'm logging the raw model response for step two, which is basically step two is the first step after planning. We're feeding the plan to a model, and it starts giving us what it thinks needed next, one by one. And as you can see, it basically says, this is my format for combination of Llama CPP and Llama 3.1 model. This is how I tell you without the guesswork that you need to make a tool call. My code understands this and makes this tool call. The same thing happens. And by the way, it actually worked pretty quick because I asked it to guess based on the name. It does not need to do any more tool calling. It needs to reason more. Let's see what it came up with. So based on the file name, it appears the files are related to project or a tool to utilize Llama models, specifically Llama 3.1, the files mix Python scripts and documentation. That's perfect, guys. I think, given that, well, some of you might say Llama 3.1 is a very capable model. In comparison to Gemma models or ChatGPT open source models, GPT OSS, Llama 3.1 is pretty dumb model, but it still does a great work for us, almost indistinguishable from real LLMs if we do proper prompt and context engineering for it, and we can clearly see an agentic behavior here. As this will evolve, um, I'm at least planning on giving more knowledge sharing sessions, first by using the third-party agentic libraries, and then showing audience something more advanced, where agent has all the safeguards and mechanism, maybe a more ingenious orchestration logic in it. But today I wanted to show you those aspects and different examples, and I think that's what I did. We can proceed to questions. Anna, please.
How compatible are different models to combine them in a chosen environment?
Yeah, that's a great question. Oh, it was probably 3 or 4 years ago when I was first experimenting with ML.NET. Agentic coding was not there yet, and in fact, LLMs were not super prominent. And I was trying to do a computer vision with ML.NET library, hoping I can do all of the AI work in C#. And that's when I learned about the Microsoft's creation called Onyx runtime and Onyx format. And uh, incidentally, it's still alive and has a very good use case in Microsoft's family of models, like models 5, 3, and 4. But like, how compatible? You can easily find the combination you need. There are distinct large players which are either coming from Meta, which is Llama family, and there is a good GGoof format which is available in abundance on Hugging Face registry, and a lot of models are converted into GGoof. If the model that you are interested in is available in this format, it will be very easy to find the inference mechanism for it, efficient for your use case. And but the notable players are basically GGoof, Onyx, and the Google proprietary inference, which is used to infer on Gemma. I don't remember its name, but basically think that there are many, and some core players are shaping. I strongly suggest you go with GGoof because almost every model which you might be interested in will be available in that format. And then Llama CPP or Llama and many other inference mechanisms work with GGoof. Sorry for the long answer. Please, let's proceed. Oh, I think so far I've been showing you the models which do not have thinking capability, and those are not reasoning models. I will greatly oversimplify this, and not afraid to say this, true fanatics in a good sense of LLMs and underlying technology will tell me that I'm saying a big lie, but reasoning is just a mechanism which is artificially engineered to ask LLM to synthetically enrich its context. That's very important. We did not talk about context engineering, which is where your software developer skills will come in most handy in the year 2026 and beyond. But reasoning models do not do anything super fancy. All they do is the smart way of take your query and try to give a little bit more internal answers to slightly pivoted questions so that they have more tokens, more words before they proceed to give you a response. And you know how people have been criticizing progress in CPU, like we hit the 3 gigahertz speed of CPUs, what, when I was probably 15, and then it's all kind of a halted, and everyone was saying, oh, those CPU developers are just creating a smaller nanometer technology, but they're not truly advancing. Well, someone can say that large LLMs are truly not advancing. They're just doing a refined training set. They are advancing in multimodality, obviously, but those reasoning things are just the fine tuning of the behavior of the model. So again, sorry, not sorry for the long answer. It's an important topic, but reasoning is not like something super special. It's more trying in synthetic context enrichment. Uh, so yes, everything I said is applicable to non-reasoning models. We are synthetically calling things reasoning, which are not reasoning.
Mhm. Thank you, Max. And there is a question that pops up every time. Could you share the source code? Will you share the source code? What do you think about sharing the source code?
Um, and obviously, yes, I will push it to a public repository on my GitHub. So ideally, and I was thinking about this morning, because again, this is the playground I wanted to show you. A more serious implementation of agents is much better planned and has more robustness mechanisms in code. And I was thinking, how, like, those coding agents like ChatGPT, or yeah, it's called ChatGPT Codex, and models from Anthropic, they always advertised as, oh, Claude Code can now go for 30 hours. And Codex was able to work 75 minutes or whatever. Obviously, though all of those are synthetic, maybe Codex is actually that good. But when it comes to the question when an agent should stop, I think in our code, ideally, we let the agent to go on. As it will approach the end of its context window, it's going to be compacting its conversation, and we should be logging it as a checkpoint. And we need to have another agent that will be reviewing the compacted checkpoints and will make a decision whether this agent is stuck and needs to be abruptly stopped or it can continue. But that's up to your imagination. You guys are the architects of the future of the agentic operation. I don't think there will be one leader. Therefore, it's important to know how the bare bones work. So I would straight go to advanced multi-agent solution for the topic of. So I'm basically saying, do not limit turns. This way, you do not limit the complexity of the task you give it, but you need the system to stop at some point. So you need another AI to stop this other guy. That's the ideal scenario that's in my head right now. Yeah, let's proceed. In terms of latency, you can simply add checks on your target environment. Let's assume you have the cloud, you have the Linux VM's GPU. You can basically log your timings and basically evaluate on latency of inference. You apply standard conventional cloud engineering techniques to evaluate latency. But there was another term. Can you repeat on evaluate on latency and what?
And
Latency. Oh, right?
And
Accuracy and late. Yeah. So accuracy is a different type of thing. Like both Anthropic and Google and OpenAI are competing with their agents. They're using what 700 billion parameter models, which are exactly 100 times smarter than what we played around with today. And still, those things sometimes hallucinate and make bad decisions. At least they were at the beginning of this year, end of spring of this year. I don't think that we can get Claude Code to output nonsense right now, unless we really spoil the context window. So accuracy it's a human QA thing for now. Obviously, again, people from more advanced companies, like not more advanced than which I'm working on, but companies which are focusing on this solely, they will say, "Come on, Max, you're saying humans should review AI agents." Well, I'm saying that, yeah, obviously you can create another agent to review the accuracy of another, but I don't think you can completely remove human in the loop for the QA activities of LLM output. That's all. I hope I answered this question.
the next one. What is your main Bible book for the how to build multi-turn agents?
No, the Bible book, and I'm so afraid to say a lot of things here. My main Bible book, or at least my workflow, is I start research with Grok. Although I have Max account on Anthropic, and I think Claude is one of the most capable models out there. Also, I opt for this stuff. I didn't read a book. I usually start with Grok for research, and then I use Claude Code to actually implement code and pivot and test whatever I have created. Um, and if I need a proper research on what's up-to-date approach of building agents, I just will ask Grok, and it will basically do a research and tell me, like any other. I'm not saying Grok is anywhere special. I'm just saying that so far my preference is Grok, and that answers the question, what is my personal Bible? There are very capable AI engineering directors in the department I work in, and they would tell you a completely different approach. I know some people are actually reading modern books and playing by the book.
How do you go about evils and observability of agentic framework products you develop?
So it is a little spoiler, but Ciklum is gonna come out with several agentic AI automation solutions, hopefully next year. We cannot be certain. And in those solutions, which are out of the box for our customers to build on top and adopt towards their need, there will be a observability suite. I have already a planned architectural diagrams, but the short answer is we're gonna exhaustively build observability system, which is partly conventional dashboard observability, partly AI agent review, but we basically develop software to implement higher observability. Depending on who the observer is, the system will be different. But I cannot give you any know-hows at this point. It's just the cost of writing code has collapsed greatly, and we can afford to build a vast systems around our agentic operations so that observability is actually achieved.
Mhm. How much does having additional final check improve the outcome? Did you measure it with the same task for the agent, running it multiple times?
Yes. The final check was approximately saving me from a hallucinating agent. And again, I probably did something with parsing logic or prompt so that us never saw this hallucination the other way into other directions. It almost, by the demos we've seen, it almost seems like the final check is redundant, but at least 40% of the time it was saving the situation. But you might think, how come it's the same model? I think that when you ask a question, this is the history, this is the answer candidate, and this is the initial query, that what reveals the model to actually say no, that completely does not address the query. Otherwise, the model is not able to, at least it was not able to provide a correct answer. But that's an important question. It's unlucky that I couldn't show you the result of the final check being different.
You missed to talk about prompt evolution. Could you brief on that? Let's start with the first one. So, prompt evolution, brief on that, and then we move to the second one.
Yeah, those are important questions. They highlight that the fact that I was a bit jumpy when I was giving you this the material, and I was always referring that you will review the Python code on your own. I still would appreciate that if you are truly interested, please do review. It won't, if you are armed with a coding assistant, it will just give you a summary within 3 minutes for that review. But um, I basically have two types of prompts in the examples. One is a more primitivistic prompt where I'm simply asking the model to follow the structure and I'm parsing the text structure. And the other one is the scripts 7 and 8, where I take a different approach and I try to explore all Llama and Llama CPP's dedicated facility to read an instruction from the model that I need to make a tool call. When I say I mean agent, not the programmer. So prompt engineering evolution, the prompt evolution is basically not critical here, although for evolving cases of agents, I will just simply making it more robust. When I was testing and seeing that something is missing from the prompt, I was adding stuff on this, not super crucial. If you want to get the most out of the time you review with source code, I think you need to review script number 8. It has the biggest prompts, it has 3 of them, and it does the proper tool calling for the combination I'm using.
Mhm. And the second question from the same participant, how does LLMs understand that a tool can do from such a simple name, like run command? How do you know you want to run a Unix command? How can we provide more info about each tool?
That's a good question. So that's what makes the LLM and this even primitive example amazing. That I tell it what time is it now, and it doesn't know what time it is but it saw in the prompt that you can call commands and you are actually running on a computer. So because in its training data, in its knowledge about the world, which are packed in those 8 gigabytes of weight, it knows the Linux commands because it's essentially an expert in Linux. It says, why not? I think in order to answer this question, I need to make a tool call. So the short answer is it's in the training data of the model, all of those commands and their descriptions.
Mhm. The next one, how do you handle if the agent overflows with tokens? Is it starting hallucinating in that case?
No, you will get an inference exception. So um, whatever mechanism you will use to do inference on your model, at some, like if you are going to be using cloud provided API, this situation is usually handled by your API. You'll simply gonna get a not even 500 error. You're gonna get an API error which basically says like usage violated. You are sending too big of a payload or whatever. So I have never gotten this locally running all Llama model to overflow, but it can easily be tested and it will throw an exception, which I simply will not read the string and my logic will not be able to proceed because I will not get the response from the model if I overflow the context. It's the job of an agent logic of the programmer to make sure we never make a call that when response is being generated for the simple call, that the context will overflow. It will throw an exception. Short answer is that.
Mhm. And here's a very personal question. How do you stay updated with all the updates and changes?
So for the past maybe even 4 years, since 2000, so I'm not very, so I read Medium articles, which are in my Medium feed. For the past maybe 4 to 5 years, I've been listening to a podcast by the guy from California called Data Skeptic, which was reviewing data science topics in general. And starting from May this year, I completely stopped listening to Data Skeptic, and I'm listening to the podcast called AI Daily Brief, which some you will easily find. I do it on the school trips when I drop off and pick up my son. And yeah, I stay up to date by reading articles and listening to AI Daily Brief. And that might not seem a lot, but it's enough for me given that I have a day job to do. Yeah, that's my answer. Easy recipe.
Mhm. What's your take on fully autonomous agents? We see human in the loop agents.
I think that, and this will be a part of a larger platform which we will be building in Ciklum, and we're not alone. The larger players are already there, with Google having the agent space and Salesforce having their own. But the blueprint of current implementation, which we're going to be doing somewhere around December, is that it will be a special instruction that agent, if you identify inability to proceed autonomously, you should, rather than not, call this command, which is basically a human input request in the dashboard. You need to call this command, which will trigger basically a webhook with a parameter, and this way we will synthetically ask agent to stop and wait for human input. Once the human input is provided in a web interface, the human is going to submit it. It's going to trigger the agent flow again, and it's going to continue with that response in its context. I don't know how I vividly explain this to you, but yes, everyone will be building fully autonomous agents. And but it's also important that, really briefly, we're working with several financial institutions, not in retail yet, but almost all the customers are also asking about local inference or small language models fine-tunable. It will be much harder to implement human-in-the-loop callbacks with dumber models. Whenever we're working with basically ChatGPT 5, it's easily gonna trigger the human-in-the-loop. Smaller models are not, so it's gonna pose an engineering challenge, but it's still overcomable. Let's put it this way.
And especially thank you for the question. Well, I see the last question is probably for me about Ciklum events. Yes, please stay in touch. We'll have more speakers corners on different topics, and it will be interesting to share knowledge and experience with you.
Guys, thank you for attending. Those of you who stayed so far, thank you for your time. I hope I was of value to you.